Welcome to Mrs. Neller's notes for her pre-calculus class. These are the notes for section 11.1 entitled Making Models Using Variation. And basically what we're going to talk about today are the three different types of variation. You can have direct, inverse, and joint variation. Direct variation is basically when you have a direct relationship between two quantities. And we have the equation y equals kx. That's our equation that we're going to have for direct variation. And k is your constant, so it's always going to stay k. And y and x are the two quantities that have a direct relationship. So they're dependent upon each other. And this is really similar to our slope-intercept form if your intercept is 0. So if you have this y equals mx part of the equation, that's just like direct variation, except there's an m instead of a k. And if your intercept is 0, then really your slope is reflected in the graph at a constant rate. Your slope is increasing at that constant rate. So there's a direct relationship between the x value and the y value, and that relationship is that slope, that constant. So we're going to go through a word problem here. And this problem is about a thunderstorm, but we're going to apply the direct variation concept to it. So during a thunderstorm, you see the lightning before you hear the thunder because the light travels much faster than the sound. And then this sentence right here is going to be really important. The distance between you and the storm varies directly as the time interval between the lightning and the thunder. So basically, that sentence right there says, if we translated it phrase by phrase, the equation that we want to use for our direct variation. Okay? And it has some keywords in here. It says varies directly. So that tells us the type of variation we're using, and then it tells us the variables that we need to substitute in for y equals k times x. So we're going to start with this basic format, the y equals k times x, since it's direct variation. But it says that the distance between you and the storm varies directly. So instead of the y, I'm going to have the d for the distance. And the k is going to stay k, that's our constant. So the distance between you and the storm varies directly, so that's my constant, as the time interval between the lightning and the thunder. So instead of x, I'm going to have t. So now that I have that equation, now I can work through part A. So suppose the thunder from a storm 5,400 feet away takes 5 seconds to reach you. Determine the constant of proportionality and write the equation for the variation. So basically we're going to plug in the information that we know into this equation that we now have, and we're going to solve for k. So my distance is 5,400. K is going to stay k, and my time is 5 seconds. So then I'm going to divide by 5 and solve for k, and k will be 1,080. So that's my constant. So I have my constant of proportionality, but then it also says to go back and write the equation for the variation. So that means I'm going to take this equation that I had with all the variables, and I'm going to substitute k into it. So d equals 1,080 times t. So that's my equation for the variation. And that's the equation that I can use now for any thunderstorm. They tell me any time or any distance, and I can tell you the other time or the other distance. Okay? Now that I have that constant of proportionality, that direct variation constant, I'm going to be able to find the relationship between distance and time, no matter how far away the storm is or how long the lightning took to get to us. Okay, so now we want to sketch the graph of that equation. I'm going to write the equation again up at the top here. It was d equals 1,080 times t. Now, if you're sketching this graph, it's going to be a pretty big graph. We've got a really big slope there, 1,080. So I would go to your graphing calculator, go to y equals, and type that equation in. When you type it into your calculator, it'll be y equals 1080x. And then go to the table feature and write down a few values for a few seconds that this storm would be traveling. So 0, 1, 2, 3. Those would be our x values that we could see on the table. Those would really be the times that it would be taking this thunder or the lightning to get to us. So at 0, it would be 0 at 0 time. This would be like when the lightning is striking, when you're seeing the flash. 1 second later would be 1080. We substituted 1 in there. If we substitute 2 in, we'd get 2160. 3, we'd have 3240. And those are values that if you put that in your graphing calculator, you can just write those down right off the table. And now that we have a few points, we can graph them. So you make your x and your y axis there. We need to label, and I'm going to use a little extra room here. Let's say we have 1, 2, and 3. So this will be my time. And we want to say that it's in seconds, so people know how we're measuring. And then we also have our distance going up the other side. So this would be my distance, and it would be in feet. And we need to go to about 3,000. So let me just, let me say every 2 boxes. That'll be 1,000, 2,000, 3,000. So it's kind of a small graph here. Could have spread it out more and used a little bit more of the space, but that's okay. We're just trying to get an idea of what's going on here. So we have 0, 0, so I get to actually plot that point, my origin. And then at 1 second, I have about 1,080, so just over 1,000, just a little bit past it. At 2 seconds, I have 21, so again, we're going to estimate just a little bit. And at 3 seconds, we have 32, so I'm going to go past the 3,000 just a little bit. Okay. And then I would connect those points. And this is a linear relationship, so technically this graph could continue on. If you put the arrow out at the end, technically that wouldn't be wrong, but usually you just plot the 3 values that we have. Okay, and then for part C, now we want to use that equation and we want to interpret it to help us find some more data. If the time interval between the lightning and the thunder is now 8 seconds, how far away is the storm? So we're still using that equation that we wrote, D equals 1080 times T. Okay, so now it says if the time is 8 seconds, so I'm going to substitute in 8 for the time. How far away is the storm? How far? That's distance. So my distance now, if I multiply those, will be 8,640 feet. But we don't usually talk about stuff being that many feet away. When you get up into thousands of feet, usually we would convert it into miles. Okay, now there's nothing in the direction that says how we need to write our answer, but I just want to remind you that there are 5,280 feet in 1 mile. And that's a unit of conversion that you probably know and have memorized. So if I did want to change this from feet into miles, I could divide the 8640 by 5280. So you could round this. It would be about 1.64 miles. So that's how far away the storm is. So technically, either answer would be perfectly acceptable. I think the miles probably makes a little bit more sense if you're actually realistically converting this. Okay, inverse variation now. This is, again, a type of relationship between two quantities. We have an x and a y, except it's not a direct multiplication relationship. It's a divisional relationship. Okay, so it says here that y is inversely proportional to x. or y varies inversely as x. That's the language that you're going to hear. And then this is the equation that we're going to be using. So anytime there's inverse variation, that means that we're going to be dividing. And it's always the constant divided by the variable x. Okay. And when you graph these, if you graph an inverse relationship, you do get this curve. You don't get a straight line like we had before. You get a curve that's going to decrease as time goes on. Okay, so let's apply our inverse variation here in example 2. We have Boyle's law, and Boyle's law states that when a sample of gas is compressed at a constant temperature, the pressure of the gas is inversely proportional to the volume of the gas. So again, right here, this last little part, these last couple of lines, that tells us the equation we're going to be using. The key words here are inversely proportional, so that tells us what kind of relationship we have. And then in front of that, it says the pressure of the gas is inversely proportional to the volume. So it's telling us what quantities are going to have that relationship. So let me go over here. We'd have y equals k divided by x as our standard form for inverse variation. But instead of the y, I'm going to have the pressure, so I'll just call that P. And I'm still going to keep k as k. That's my constant. So the pressure is inversely proportional to the volume. So instead of x, I'll have V. So that's my equation that I'm going to be using now in part A. It says suppose that the pressure of a sample of air that occupies 0.106 cubic meters at 25 degrees Celsius is 50 kPa. Not really sure what units that are, that is. But regardless, we want to find the constant of proportionality and write the equation for the inverse proportionality. So this is like what we did before. We're going to find our constant, and then we're going to rewrite our equation with that constant in it. Okay? So it tells me that the pressure is 50. So instead of the P, I'm going to substitute in the 50. I'm going to keep the K a K. And then it says that the volume, now I know meters cubed, I know that's got to be volume. So that's 0.106. So now I multiply both sides of this equation by the 0.106. So I could solve for K. And K is going to come out to be about 5.3. So that's my constant. And now I need to rewrite my equation. I'm going to rewrite the equation with the P and the K and the V. So my pressure will be inversely proportional. So I'm going to put that constant in there, inversely proportional to the volume. So again, this is my equation that I can use now for any relationship with Boyle's law for this sample of air. And then in part B, it says if the sample expands to a volume of 0.3 cubic meters, find the new pressure. So I'm going to use my equation, P equals 5.3 over V. That says the volume is now going to be this. So originally we had a volume of 0.106, now the volume's changed. So I'm going to substitute that in. So 0.3. And when I divide, I'll get about 17.67. And kPa was the units they were using for the pressure. Okay, last concept then is joint variation. And this is very similar to direct variation, except now instead of having two elements that have a direct relationship, now you have three or more. So here's our equation now that they're going to use. So you have z equals k times x times y. You could also have y equals k times x times z. It doesn't necessarily matter what the variables are, but remember k is going to be that constant, so that's going to stay there. and then it's going to have two variables that are being multiplied by it. Okay. Now, we can also have a relationship where one quantity is proportional and one quantity is inversely proportional. So you can have a combination of um, direct and inverse variation in a new joint variation problem. So when we have that sort of situation, then this is the type of equation that you would be working with. And you could also write it z equals k times x all divided by y. You could think of it that way too. Okay, so example 3, let's figure out what type of joint variation we have going on here. Newton's law of gravitation says that two objects with masses m1 and m2 attract each other with a force that is jointly proportional. Okay, there's my key vocabulary. To their masses. And inversely proportional to the square of the distance between the objects. Express Newton's law of gravitation as an equation. Okay, so basically they want us to take this statement up above and write it as an equation. Okay, so let's read through it again. Newton's law of gravitation says that two objects with masses, okay, attract each other with a force that is, okay, so here we go. Here's where we're starting. We're starting with the force right here. The force is jointly proportional to the masses. Okay, so force, let's use F, is jointly proportional to their masses. So I need my constant in there. And then I'm going to multiply by their masses, and they call the masses M1 and M2. So I have a joint relationship there. So remember, that's all multiplication. And that force is also inversely proportional to the square of the distance between the objects. So the square of the distance. So now that I have an inverse proportional relationship here, I'm going to divide. And the square of the distance. Now be careful now, it doesn't say square root. It says square of the distance. So I'm going to have my variable r, and I have to square it. Now, your book might call the constant something else. I mean, it's a law of gravitation, so they might use g for the constant. I'm not going to be super duper picky about what variable you use for the constant. So this would be completely acceptable to me. The other way the book might write the answer is they might take that constant and they might pull it out front. So you might see it written like this. F equals k times, and then m1 times m2 all over the r squared. So they take that constant and they pull it out from that fraction and make it a single term out front. Okay, I like to think of it as this first formula where it's all one big fraction, because that's just easier for me to mentally grasp. So there are some problems for you to practice these concepts. Hopefully this is a little bit of review. You should have seen these types of variations before. But the combo where you can have multiplication and division in the same equation, that can be a little tricky. So just make sure you read those word problems carefully. And if you have any questions, come on by and see me before school.